Hello everyone, and welcome back. Today we're going to continue our exploration of differentiation and introduce a method known as implicit differentiation. Just as a forefront note, I highly recommend being comfortable with the chain rule, product rule, quotient rule, and your elementary derivative formulas before diving into this. Once you're comfortable with those, and also comfortable with implicit differentiation, there's pretty much no function or relation for which you cannot differentiate. So, if you're a master of each of these techniques, someone can give you a function that looks extremely complex and practically difficult, but theoretically you should be able to still be able to find the derivative of it, and technically speaking, any higher order derivative of it as well, although it probably is going to be tedious and very time consuming. So the idea behind implicit differentiation is practically this, and we'll leave the theoretical and rigorous proof and statement of this theorem for a later time. But let's assume that we have two relations f and g that belong to two-dimensional space R2, and let's assume that they are going to be equal to each other for all points x and y located in their specified domains. So, if they are equal to one another, in a sense they must change the same exact way at all points p that belong to their domain. That is, we can take the derivative of both sides of this relation with respect to x, or technically speaking, we can also take the derivative with respect to y, or theoretically any variable, regardless if it's the variable in its domain or not. Let's just briefly mention a subtle point for one of the derivative formulas that we discussed before, but this is going to make a lot more sense later when we start introducing multiple variables. So let's assume we have the derivative of x squared. You should already know that it's equal to 2x, but I'm going to write it in a different way. So I'm going to write this as the derivative of x, the quantity squared, and I'm going to look at this as a chain rule problem. So obviously the square is controlling that linear function, so that's going to be the derivative of something squared, which is obviously going to be 2 times something, and then we're going to take the derivative of that interior function, which is the derivative of x. And then obviously that's going to be equal to 2x times, so d over dx of x can also be rewritten as dx over dx. Now regardless of how small or infinitesimally small that dx is, notice that we have the same infinitesimal on top and bottom, therefore that's going to be equal to 1. So we're just going to be left with 2x times 1, which obviously is 2x, which is the original answer, just by using the product rule. But notice that the only reason that this term sort of disappears is that we have a differential of x on top and a differential of x on bottom. If they're different differentials, they will not cancel, and it just stays as it is. For example, if somebody asks you what is the derivative of x squared with respect to y, similarly speaking, that's going to be 2x times the derivative of x with respect to y, but here the correct answer is just 2x times dx over dy, because the dx over dy does not cancel. Now that we've discussed the basics, now let us jump into our first example of implicit differentiation. Let's consider the relation in R2 that consists of all points x, y that satisfy this relation, x squared plus y squared equals 1, which you should already know is the equation of a unit circle, in particular a circle of radius 1, centered at the origin 0, 0, and has a graph as shown on the right. So let's pick an arbitrary point on this circle that we know for sure is here. In particular, let's choose this point here where this point is 1/2 comma the square root of 3 over 2. Right? And you probably know what angle theta is corresponding to this, but that's actually not my point for doing this. So if we consider a line to this circle that is tangent to the curve at that point, obviously that line has a slope. So my question to you is this: what is this slope equal to? So keep in mind, if two relations, x squared plus y squared, and another relation, 1, are equal to each other, then the derivatives will be equal to each other at all points that belong to the equality of their relations. So what I'm going to do is I'm going to differentiate both sides of this equation with respect to x. So I have the derivative of x squared plus y squared with respect to x, and then the derivative with respect to x of 1. Now the reason that I'm taking the derivative with respect to x here is because the slope is the derivative with respect to x of y, aka dy over dx, or our rise over run interpretation of slope. Now, if you're interested in dx over dy, you'd probably want to do the derivative with respect to y instead. Anyway, since we're going for a derivative with respect to x term, we're going to differentiate with respect to x. So as usual, we already know that derivatives can distribute over addition, so we have that. And the derivative of this constant on the right-hand side is just going to be equal to 0. So on the left-hand side, we're going to have the derivative of x squared, which is going to be 2x, and the derivative of y squared is going to be 2y times the derivative of y with respect to x from the chain rule and that little example that I did earlier. And as already mentioned, the derivative of 1 is going to be equal to 0. Keep in mind, what we're looking for is the derivative of y with respect to x, which is located right here. So I just need to solve this equation for that differential quotient dy over dx. So I can obviously subtract 2x from both sides, and then divide both sides by 2y. And then I'm going to have dy divided by dx is going to be equal to minus 2x divided by 2y, which will be equal to minus x divided by y. Obviously, you cannot put any pair of numbers x, y into this relation. That pair must also satisfy the original relation x squared plus y squared is equal to 1. So you cannot plug in 5 and 5 for x and y respectively because 5 squared plus 5 squared does not give you 1. Right? But we do know that the point 1/2 minus square root of 3 over 2, which I'm going to call the point P, does belong to that relation. Therefore, I should find dy over dx at that point P. So once I do that, we're going to have the derivative of y with respect to x at the point P is going to be equal to minus, so the x value is going to be 1/2 over the y value, which is the square root of 3 over 2. And that's going to be equal to minus, so those 2's will cancel, so we're going to have minus 1 over the square root of 3, which some people will also prefer to write as minus the square root of 3 over 3. So that's going to be the slope of that particular tangent line. So what if somebody asks you, well, what is the equation of that tangent line? Well, if we know the slope, which I'm going to abbreviate as just m, then we have that the equation of the tangent line, I'm going to call that yt, is going to be equal to m x plus some intercept term b, right? So the point we have is 1/2 square root of 3 over 2, so I'm just going to substitute that for y and x. So that's going to give me what? So the y value is going to be equal to minus square root of 3 over 3 times the x value plus our vertical intercept b. And then what I can do is I can add the square root of 3 over 6 to both sides, right? And then obviously I need to multiply that by 3 to get a common denominator there, and that's going to give us our b. So b is going to be equal to 3 square root of 3 over 6 plus the square root of 3 over 6, and that's going to be 4 square root of 3 over 6, right? And that is going to be our intercept term. So once we have our intercept term, we can formally state our equation of our line that is tangent to the curve at that point P, and that's going to be equal to y is equal to m x plus 4 square roots of 3 over 6, and that is the equation of our tangent line. Let's do a couple more examples just to make sure we're comfortable with the mechanics of implicit differentiation. So let's assume we're interested in finding dy over dx, and keep in mind dy over dx is just another way of saying the derivative with respect to x of the term y, right? So obviously we need to apply a x derivative operator to both the left and the right hand side, and then solve that resulting expression for dy over dx. So here's our relation. So I'm going to have the derivative with respect to x of x squared minus y squared, and that's going to be equal to the derivative with respect to x of x cubed plus y. So once I distribute that derivative over those differences and sums, then I'm going to have 2x minus 2y times the derivative of y with respect to x is going to be equal to 3x squared plus the derivative of y with respect to x. Again, it's just going to be dy over dx. So now I have these two dy dx's in my equation, so I need to isolate them and solve. So I'm going to add 2y dy over dx to both sides, and I'm going to subtract 3x squared on both sides. And I'm going to have, what is that going to give me? Let's see, we're going to have dy over dx plus 2y dy over dx is going to be equal to 2x minus 3x squared. So once I have that, then I can factor out this dy out of dy over dx term out of the left-hand side. I'm just going to be left with 1 plus 2y dy over dx on the left-hand side, and then I can divide both sides by 1 plus 2y on the left-hand side and the right-hand side, and that gives me my expression for dy over dx. So I'm going to have dy over dx is going to be equal to 2x minus 3x squared, all divided by 1 plus 2y. And obviously that will be our final answer, but you could probably factor this into a more desirable form. For example, you can write this as dy over dx is equal to x times 2 minus 3x all over 2y plus 1. I guess it would be a more preferred form, but nonetheless, they are equivalent. Obviously, that example is a little bit more easier, so let's just do one just for excitement that's a little bit more complex. So let's assume that the relation that we're interested in is 3x squared minus 2xy plus y to the power of 4 is going to be equal to 5x cubed minus y squared plus the sine of y. And let's assume that we're interested in finding dx over dy. Right? So instead of differentiating with respect to y, we can actually differentiate with respect to x, find dy over dx, and then reciprocate that answer to get dx over dy. So in some sense, dx over dy is just the reciprocal of differentials of dy over dx. Right? So let's just differentiate with respect to x. So I'm going to differentiate left and right with respect to x. And that's going to give me 1. Now be careful when you get to this 2xy term because that's going to be a product rule, right? So what is that going to give us? So it's going to give us 6x minus 2. So we have first times the derivative of the second. So the derivative of the second is going to be dy over dx. Just for shorthand notation, I'm just going to be notating that as y prime, right? So it's the first times the derivative of the second plus the second times the derivative of x, which is 1. And then we're going to have 4y cubed times the derivative of y with respect to x. And that's going to be equal to 15x squared minus 2y times the derivative of y with respect to x. And then cosine of y times the derivative of y with respect to x. All right? Now, let's clean this up just a tad bit by distributing our 2 in. So we're going to have 6x minus 2xy prime minus 2y plus 4y cubed y prime is equal to 15x squared minus 2y prime plus cosine y prime. Now what I need to do is I need to get my y prime terms to the same exact side. And what I'm going to do is I'm going to shift these two to the right hand side, and I'm going to shift this 15x squared to the left hand side. And once I do that, what will I have? So I'm going to have 6x minus 2y minus 15x squared on the left-hand side. And on the right-hand side, I'm going to have 2xy prime minus 4y cubed y prime minus 2y prime plus cosine y prime. And every single term on the right-hand side should have a y prime in it, else there's something that's going to be, sort of incorrect here. So once I have that, then I can factor out my y prime out of the right-hand side and divide by the sum and difference of the terms that precede them. So once I do that, I'm going to have y prime, which is just another way of saying dy over dx, is going to be equal to the left-hand side, which is going to be 6x minus 2y minus 15x squared, all over 2x minus 4y cubed minus 2y plus cosine y. Okay, so that is my answer for dy over dx, but that's not what we were looking for. We were looking for dx over dy. So that's going to be equal to what? So what I actually want to do, because I don't like all these negative signs, I'm going to multiply top and bottom by -1 just for clarification, because sometimes I like my leading term on the top or bottom to have a positive exponent, and both of them are negative, so yeah, it's just a preference. So that's going to give us, on the bottom, 15x squared plus, let's do 2y minus 6x, and on the top will become positive 4y cubed Let's do positive 2y minus 2x, and then we're going to have a minus cosine y on the top. And that is our answer for the equation of differentials, dx over dy, in that order. Now that we have the basics of implicit differentiation discussed, let's introduce several of the other rules that actually come as a result from implicit differentiation. One of the more common ones would be inverse trigonometric and inverse hyperbolic functions and their derivatives. So in case you don't know what an inverse trigonometric function is, let's just go over the basics. For example, let's assume that we have the function y is equal to sine of x, which is given to be here. So this is y is equal to the sine of x. And let's assume we want to graph the relation x is equal to the sine of y, which is sometimes abbreviated as y is equal to the arc sine of x. Some people will use just a sine of x, or a notation that I'm not personally fond of, sine with a minus 1 of x. I'm going to be using the first. To avoid any ambiguity with other things. So what does this relation look like? So obviously instead of riding along the x-axis, it's going to be riding along the y-axis, and it's going to have this particular shape shown in pink. Right? So obviously this curve definitely does have some tangent lines and some slopes associated to them. So I should be able to have a closed form representation. So I give you the value of x, for example. I give you this particular value x, and obviously there's several infinitely many tangent lines that are associated to them, but notice that they all have the same exact slope provided that I have drawn this correctly, right? So I should be able to find a function where I plug in the value of x, it gives me those slopes. So how am I going to go about this? All right. So y is equal to the arc sine of x. What is my derivative equal to? So the first thing I'm going to do is I'm going to take the sine of both sides. So I'm going to have the sine of y is equal to the sine of the arc sine of x. Since they are inverses, those are going to cancel. So I'm just going to be left with the sine of y is equal to x. Now I'm going to perform implicit differentiation, so I'm going to have the derivative with respect to x of the sine of y is equal to the derivative with respect to x of x. So the derivative of sine y with respect to x is going to be equal to cosine y times the derivative of y with respect to x, and the derivative of x is just going to be equal to 1. And now I'm going to be solving for dy over dx, so I need to divide both sides by cosine y. And then I'm going to have that dy over dx is equal to 1 divided by cosine of y. And you may think, okay, that's my answer. But notice that this should be a function of x, not a function of y. So we need to do some algebraic trickery in order to get that into the form that we want. So recall that the sine squared of y plus the cosine of y must be equal to 1. And if we solve this expression for cosine of y is just going to be equal to 1 minus the sine squared of y, right? But keep in mind what the sine of y is. The sine of y is equal to x. So I can just replace that, and I'm going to have the cosine of y is going to be equal to the square root of 1 minus the sine of y, which is just the same thing as x, squared. So therefore, I have that dy over dx is also written as 1 over the square root of 1 minus x squared, right? But what was dy over dx? Dy over dx was the derivative of the arc sine of x, right? And that is our lovely answer, right? And obviously the domain of this function is all x belonging to the interval minus 1 to 1, right? Because when it's equal to minus 1 and 1, that gives us a vertical tangent line, which is obviously not a finite slope. So that proof isn't too bad, but similarly, you can show that the derivative of arc cosine of x will be equal to a similar function, minus 1 over the square root of 1 minus x squared, same domain. So the only difference between the derivative of arc sine and arc cosine is that negative 1 on top. Let's do another example and sort of see if we can get the answer. So let's do the derivative of arctangent of x. Now arctangent of x is actually quite a nice function. It has two horizontal asymptotes, one at y is equal to pi over 2, the other at y is equal to minus pi over 2, and sort of has this S-shaped looking thing, similar to the cube root function, but it's bounded above and below by those horizontal asymptotes. So obviously this has some slope and some tangent lines, and it's actually more behaved compared to arcsine and arccosine. So what is the general expression? So if I were to give you, this particular value of a, what is the slope of that tangent line? So this answer should give that to me. So I'm going to start by defining y is equal to the arctangent of x, and obviously my goal is to find dy over dx. I'm going to begin by taking the tangent of both sides. So I'm going to have the tangent of y is equal to the tangent of the arctangent of x. But tangent and arctangent are just inverses, so those are going to cancel each other out. So I'm going to have the tangent of y is equal to x, and then I'm going to take the derivative with respect to x of both sides of this relation. So if you don't remember, the derivative of tangent y is the secant squared of y, and then by the chain rule we have that dy over dx term, and then we're going to have a 1 there. And then dividing both sides by secant squared y, we have our dy over dx term. So dy over dx will be equal to 1 over secant squared y. But we want a relation that's a function of x, not a function of y. But if you remember from trigonometry, 1 plus tangent squared y is secant squared y, and y is the same as what? Well, we know that tangent y is equal to x, so we can just replace that in this expression. So we have just 1 plus x squared is equal to secant squared of y. And we can just replace that into that identity. So we have the derivative of y with respect to x is equal to 1 over 1 plus x squared, which is actually the derivative of the arctangent function. Right? So it's actually this thing. And this function actually looks sort of like a bell curve, which is actually pretty interesting. And as a similar exercise, you can show that the derivative of the arccotangent function will just be equal to -1 of 1 over -1 over 1 plus x squared. Right? So those are the derivatives of arcsine, arccosine, arctangent, and arccotangent. So we have two other trigonometric functions to discuss. Let's do secant. So y is equal to the arcsecant of x. What is its derivative? So let's just give a quick graph of this. So this graph may look a little strange. Right, so we're going to have a horizontal asymptote of pi over 2. -1 and 1 are going to be focal points. And then we're going to have our right part of the curve there. And that's obviously a horizontal asymptote. And let's extend this y-axis just a little bit more. That's pi, that's 0. And what we're going to have is a closed dot there at -1 pi. And this is going to come down. So that's the arcsecant function. Obviously the domain is -∞ to -1 and 1 to positive infinity. And the derivative typically is not going to be defined at those endpoints because it's approaching a vertical asymptote. So what we're going to do is we're going to take the secant of both sides. So we're going to have the secant of y is equal to x, and then take the derivative with respect to x of both sides. So we're going to have the secant of y, tangent of y, dy over dx is equal to 1. And then we're going to have dy over dx will be equal to 1 divided by secant of y, tangent of y. So firstly, we know that secant of y is equal to x, so I can write that as 1 over x times tangent of y. And now we need to get rid of that tangent of y. So remember that 1 plus tangent squared y is equal to secant squared of y, or 1 plus tangent squared y is equal to x squared. And I just need to solve this equation for tangent. So tangent of y is going to be equal to the square root of x squared minus 1. So therefore, dy over dx will be equal to 1 over x times the square root of x squared minus 1. And that would be its derivative. And obviously, x must belong to this interval minus infinity to minus 1 to 1 to infinity, which I'm just going to call the complement of minus 1 to 1. Right, so everything outside of that interval. And similarly, just as a fun exercise, what do you think the derivative of arc cosecant is? That's going to be equal to minus 1 over x times x squared minus 1. Now, we have 6 hyperbolic trigonometric functions. Hyperbolic sine, cosine, hyperbolic tangent, cotangent, hyperbolic secant, cosecant. And all of them have their rules, so let's just quickly go through them. We're not going to prove them, but I leave to you as an exercise to show that they are indeed what they are. So the first is the derivative of arc hyperbolic sine of x. And this is going to be equal to 1 over the square root, and I think the best way to write this would be x squared plus 1. The derivative of arc hyperbolic cosine will be equal to 1 over the square root of x squared minus 1, and this is only defined for x is bigger than 1. The derivative of arc hyperbolic tangent. So for tangent, it was 1 over 1 plus x squared. This time it's 1 over 1 minus x squared. And this is defined for absolute value of x is less than 1. And then we have the derivative of arc hyperbolic cotangent of x. And this is going to be equal to 1 over 1 minus x squared, but this is defined for absolute value of x is bigger than 1. So they have the same exact sort of derivative, but they're defined on different domains. And that's actually due to how inverse hyperbolic tangent and cotangent are defined. And for the last two, so the derivative of inverse hyperbolic secant or arc sec of x, this is going to be equal to negative 1 over x times the square root of 1 over x squared, and this is defined for x in the interval 0 to 1. And the derivative of its friend, arc hyperbolic cosecant of x, is equal to minus 1 over the absolute value of x times the square root of 1 plus x squared, for x is not equal to 0. Wait a minute, no, that should be 1 minus x squared. Now, something very, very interesting to notice about this is that the inverse hyperbolic secant and inverse hyperbolic cosecant both have a negative 1 on top, which is actually a little bit different compared to the circular hyperbolic secant and cosecant inverse functions, because the left-hand column was practically all positive coefficients and the right-hand column was all pretty much negative coefficients. So that's where the negative coefficients lie, and they're both on inverse hyperbolic secant and inverse hyperbolic cosecant. And obviously with these rules you can do actually quite a few things, which we won't get into here. Now that we've introduced quite a few new rules that implicit differentiation gives us in regards to inverse, circular, and hyperbolic trigonometric functions, let's do a couple examples of working backwards to sort of see what we can actually get from them. So let's assume that I ask you, okay, the derivative of arc tangent of ax, let's assume that a is a real number here, so let a be a real number. What would that be equal to? So we know that the derivative of inverse tangent is 1 over 1 plus x squared. So by the chain rule, this is going to be equal to what? So it's going to be equal to 1 over 1 plus something squared times the derivative of that something, which is the derivative of ax, which is a. So we can actually write this as a divided by 1 plus a squared x squared. And we're going to be using this identity for the next few examples. So let's see if you can guess what these functions are. So example 1. The derivative of something is equal to 5 over 1 plus 25x squared. What is that something equal to? And you can maybe pause this video to sort of think about it if you don't already know the answer. But you should see that this is just a direct usage of this formula, right? So the derivative of arctangent of a constant times x is the constant over 1 plus constant squared x squared, which is exactly here. Because notice that we can rewrite this expression as 5 over 1 plus 5 squared x squared. So this is going to be equal to what? So we're going to have the arctangent of 5x, and obviously there could have been a constant there at the end that is added because that would just differentiate to 0. So that would be its arbitrary, what some people call the antiderivative of 5 over 1 plus 25x squared. Let's look at a couple more fun examples. Suppose that we have the derivative of something is equal to 1 over 1 plus 7x squared. So obviously we have constant x squared there, so we can do some fun algebraic manipulations to that. So that's going to be equal to what? So we're going to have obviously 1 plus the square root of 7 squared x squared, and we need that square root of 7 on top, so I'm just going to introduce that to top and bottom to sort of get that out there. So once we have it in this form, we can actually see the answer, because now we see that, oh, that's equal to 1 over the square root of 7 times the arctangent of the square root of 7x plus c, and that would be our answer. Because of that constant in the right, the derivative is just going to slip over that constant anyway, so that's pretty much why it's sort of hanging in the front of both the original problem and the answer that precedes the differentiation step. Right? So let's make this just a tad bit more fun. So what is the derivative of something, and let's assume that you answer that question with 3 over 4 plus 5x squared. Maybe you want to pause this video and sort of see if you can figure this out, because it requires just a bit of cleverness. So I'm going to first off manipulate this expression just a tad bit, and I'm going to factor out a 4 out of this entire bottom so I can get a 1 plus something there. So once I do that, I'm going to have 3 over 4 times 1 plus 5 over 4 x squared, because we know that that 1/4 is just going to chill in the front anyway. And then I'm going to pull that 3 in the front constant as well. So I'm going to have 3 over 4 times, now let's focus on this. So it's going to be 1 plus the square root of 5 over 2 squared x squared, and that's obviously the constant that I need on the top. So I'm going to have the square root of 5 over 2, and I'm going to have 1 over the square root of 5 over 2 here. So I'm going to just write that as 2 over the square root of 5, right? So that's going to cancel out to 1. And this is then our arctangent relationship. So we can see that y will be equal to, so that can cancel, so that's just going to be 3 over 2 square root of 5 times the arctangent of the square root of 5 over 2x plus some arbitrary constant c. Right, so that's super exciting. And let's just do one more just to practice. So let's assume that the derivative of some unknown function is equal to 4 over 7 minus 9x squared. So here we have a minus sign. Now what I'm going to do is I'm going to begin by still taking out that 7. So I'm going to have 4 over 7 times 1 over 1 minus 9/7 x squared. And obviously I'm going to square root that and then square it, and that's going to introduce which constant I have here. So that's going to be equal to 4/7 times, so I'm going to have the square root of 9 over 7 on the top, and the square root of 9 over 7 on the bottom, the reciprocal of that. And then I'm going to have 1 minus the square root of 9 over 7 squared x squared. Now this front constant is actually quite ugly, so I need to play around with that before I move forward, because that's the same as 4 over 7 times the square root of 7 all over the square root of 9. And you could probably leave this as is. I don't know, it really depends on your preferences. Yeah, I'm just going to leave that as is. So I'm going to have the square root of, oh no, because the square root of 9 is equal to 3. So that's actually pretty nice. So I'm going to have, what is that? 3 over the square root of 7? Yeah, it's okay. Yeah, just write it as 3. So that's going to give me what? So on the top, we have 3 over the square root of 7. This doesn't matter really. And then 1 minus 3 over the square root of 7. And then squared, obviously. X squared. And that's going to set us up for our answer. Now, what about this minus? So remember, what function's derivative is just the same thing as arctangent, just a minus sign. You should remember that's inverse hyperbolic tangent. So that's going to be what? So we're going to have y is equal to 4 square root of 7 all over 21 times the inverse hyperbolic tangent of 3 over the square root of 7x plus some arbitrary constant c. And this is just some practice problems on working backwards using these formulas that we've presented. The last thing I want to introduce today is another method that comes as a result from implicit differentiation, and is known as logarithmic differentiation. So let's take a guided example of a function where logarithmic differentiation actually comes into play. In particular, the function y is equal to x to the power of x, and some people will sometimes write this as the second tetration of x. Also not common, but sometimes preferred, because you could have x to the x to the x to the x to the x, the fifth tetration of x or something like that. So how are we going to take the derivative of this? So differentiate with respect to x, right? So keep in mind the derivative of x to the x is not equal to x times x to the x minus 1, because it's not a power rule. The derivative of x to the x is not equal to x to the x times the natural log of x, because the base is not a constant. So it's neither one of these. So it's a combination of variable in the bottom and variable in the top. So how are we going to deal with this? So I'm going to start off by taking the natural logarithm of both sides of this expression. So the natural log of y is equal to the natural log of x to the power of x. And I'm going to use our properties of logarithms, and I'm going to bring that other x down. So now I'm going to have the natural log of y is equal to x times the natural log of x. And now I'm going to use our differentiation tricks and differentiate both sides with respect to x. So I'm going to have the derivative of natural log of y, so it's going to be 1 over y times dy over dx is equal to first times the derivative of the second plus the second times the derivative of the first. So let's clean this up a bit. And actually, let's multiply both sides by y. So I'm going to have dy over dx is equal to y times, so x times 1 over x, that's just going to be 1. And then we're going to have the natural log of x there. But keep in mind, what was y? Y was defined to be x to the x. So we just replace that here, and that's going to give us our answer. So dy over dx is going to be equal to x to the x times 1 plus the natural log of x. And that is our factored answer for the derivative of x to the x. Now, it doesn't have to be just used on tetrations or any fancy things like that. You can actually use this to bypass the product and chain rule on occasions, and sometimes this is actually preferred. So let's assume that we have y is equal to x squared minus the sine of x all over 1 plus the arc tangent of x. And let's actually use logarithmic differentiation to solve this equation. So to start, I'm going to take the log of both sides. So I'm going to have the natural log of y is equal to the natural log of the quotient. So remember, the natural log of a over b is the same as the natural log of a minus the natural log of b. So that's going to be equal to the natural log of x squared minus sine x minus the natural log of 1 plus the arc tangent of x. Now I'm going to differentiate both sides of this expression. So I'm going to have the derivative of natural log of y is going to be 1 over y times dy over dx. So I'm going to have dy over dx here. But what I'm going to do is I'm actually going to multiply both sides by y just to get rid of it. So dy over dx is going to be equal to y times the derivative of that minus the derivative of that term. So the derivative of natural log of something is going to be that something on the bottom, and then that derivative on the top, and then minus, so what's the derivative of 1 plus arctangent? Well, we already know what that is, but let's put our 1 over arctangent x on bottom, and the derivative of 1 plus arctangent is just going to be 1 over 1 plus x squared. So I'm actually just going to put that over on the edge so I don't have a fraction over a fraction, but that is our answer Just don't forget to replace that original y into that, but that would be your answer without having to do any fancy factoring or anything like that, which you may be required to from the perspective of the quotient rule if you chose to do about it in that fashion. So let's assume that we want to take the derivative of the third tetration of x, i.e. the derivative of x to the x to the x. Now before we go into this example, let's just recall what the derivative of the second tetration of x was equal to. So it was this x to the x times the natural log of x plus 1. Well, if we expand that, that's just going to be x to the x times the natural log of x plus x to the power of x. We're going to use this here to save a lot of unneeded steps, but let's begin by taking the natural logarithm of the function of interest, which is x to the x to the x. So once we do so, we're going to have the natural log of y is equal to the natural log of x to the power x to the x. Keep in mind, x to the x is the power of the base, therefore that is what's going to be drawn down. So we're going to have the natural log of y is equal to x to the x times the natural log of x. Once we have that, the hard work is done, and now we can apply our implicit differentiation techniques. So taking the derivative, we're going to have 1 over y times y prime. So dy over dx is going to be equal to y on the right-hand side. So the first times the derivative of the second plus the second times the derivative of the x to the x term, which keep in mind was x to the x natural log of x plus x to the x. And this can actually be cleaned up quite a bit if you are careful. So what do we have here? So keep in mind dy over dx. Y is the same as x to the x to the x. So we have x to the x times 1 over x, and then plus we have x to the x times the natural log of x to the quantity squared, plus x to the x times the natural log of x. And if you notice here, we have the x to the x term in all three of these, so we can actually just factor that out. So once we do that, we're going to have that dy over dx is equal to x to the x to the x times x to the x times, and I'm going to write the interior as so, the natural log of x squared plus the natural log of x to the power of 1, and then plus 1 over x, right? So that would be probably one of the more nicer answers you could write. Or you could write dy over dx is equal to the third tetration of x times the second tetration of x times the natural log of x squared plus the natural log of x to the first plus the natural log of x prime, I guess you could say. But this is the derivative of natural log of x in this, guys, right? Which we know to be 1 over x. So those are some of the basic applications and mechanical skills that you definitely should be able to come across when it comes to implicit differentiation and of course logarithmic differentiation and several other formulas associated to, for example, inverse trigonometric functions and inverse hyperbolic functions that sort of come across from these same tricks. So up to this point, if you're comfortable with that and the chain rule, quotient rule, and product rule, there should be no function, as long as it's elementary and you know the basic derivatives of it, that you cannot take the derivative of. Hope you enjoyed this video, and I'll see you in the next couple of examples videos where we go through several different examples of various difficulties of calculating derivatives just for your practice. Hope to see you there. Take care.